I'm sure you know. So all good? Yeah. All right. So
Yeah, just a sec. It's
sorry.
okay. Okay.
Yeah.
You can go.
All right. Yeah. So the talk will be about this new paper we have, which was accepted now for NeurIPS this year, which is called, well, it's not called this, but it's about Argmax flows and multinomial diffusion, where we model categorical data using flows and diffusion models. So here's the paper, the abstract. So let's try to see like what it is about by looking at what is this here. So generative flows and diffusion models have predominantly been trained on ordinal data, so like images and audio. And we introduce in this paper two extensions, one for flows and one for diffusion models, such that they work for categorical data. So those are called Argmax flows and multinomial diffusion. And the Argmax flows are defined by a composition of some normalizing flow and some function, Argmax function, that kind of makes the samples discrete. And then we learn a probabilistic inverse for that Argmax function that lifts the categorical data back to a continuous space. For the multinomial diffusion, on the other hand, we add categorical noise in the diffusion process, and then we learn to kind of invert or denoise that. So we learn to undo the noising process. And we show in the results that it works reasonably well for modeling text data and image segmentation maps. So this is joint work with Emil Hoekeboom, Priyank Jaini, Patrick Foray, and Max Welling, who are all at the University of Amsterdam, or Max, I guess, have actually left there now, and is at Microsoft Research. But yeah, and yeah, for Didrik Nielsen, that's me. So I'm a PhD student at the University of Denmark, working on normalizing flows and related things. So yeah. So motivation. Why do we care about this? On one hand, we have abundant high-dimensional categorical data. So one is text, the NLP domain. There's lots of applications of that. Molecules could be one other type of categorical data, like what type of atom is in the molecule. There's some discrete structure there. And this is quite important for science, if we can learn to model molecules well. Also related to that, proteins, these large biomolecules that also have a discrete structure in them, and also DNA could be modeled as a discrete sequence. So all of these are kind of important for science. You can think of also many, many more types of data, but yeah, there are lots of important types of categorical data. On the other hand, the typical models for these types of data are autoregressive models, and they are slow. So they are defined by decomposition of the dimensions in some ordering, and then you use typically a category like conditional categoricals for each dimension, and then you parameterize this typically using some, for example, an LSTM, or now popularly transformers and so on. So GPT is an example of this for text data. But while they do have fast training, so you can evaluate the log probability in one forward pass for your mini batch, so that allows you to train it quickly. It has slow sampling. So when you want to generate new samples, it requires D forward passes when you have D variables. So that means, for example, in GPT, generating a sentence is very expensive, because each subword you're generating, you have to do one forward pass in the transformer model. So the idea, or the motivation, is, can we find other models for categorical data that do not have this slow sampling? So before we move on, I just want to make this distinction clear because it will show up again and again in the talk. We can separate discrete data into two different types of discrete data. One is ordinal. So that's where you have ordered categories, where it could be like 1, 2, and 3 is low, medium, and high. So there is an order to those categories. That's what you have, for example, for images and audio, where the pixel intensities are typically from 0 to 255, and 0 is black and 255 is white. And similarly for audio. On the other hand, you have categorical data, and these have unordered categories. So, for example, text or molecules and so on. So in text, you have typically characters or words, or it could be subwords. And there is no inherent ordering of these. You just randomly assigned some discrete value, some integer to them. And that's our focus in this paper. So the outline of the talk, I will talk about these two parts. Flows for discrete data. So the background here is normalizing flows. Just the basic, like continuous, the usual normalizing flows. Then discrete flows, which try to do this using discrete transformations. And then I'll introduce surjective flows, which are deterministic in one direction and stochastic in the other. And this will naturally lead us to our main contribution, which is Argmax flows, which is a type of surjective flow. After, I will talk less about this part, but the other part will be on diffusion models for discrete data. So here I will just introduce diffusion models first. What are they? Very like high level, how do they work? And then talk about how does multinomial diffusion differ from that? What is new there? Which is our contribution again. So these two models are kind of separate. So this was also the main criticism of all reviewers, and it's kind of true. There is nothing relating them apart from the fact that they are trying to solve the same task, and that is modeling high-dimensional categorical data. So therefore, I talk about just Argmax flows first, and then about multinomial diffusion next. So normalizing flows. Most of you, or some of you, maybe know how this works already, but you have a simple base distribution, typically like a Gaussian in the set space, and you use some deterministic mapping F that maps samples from this to the data space X. That gives you a more flexible distribution here. And importantly, for normalizing flows, this transformation is invertible, so you can compute F inverse. And because of that, you can compute the density using the change of variables formula. Yeah. So that requires you to map your mini-batch X to the latent space, evaluate that under the base distribution, the Gaussian, and then add a Jacobian determinant term that accounts for volume change in that transformation. So can we have flows for discrete data? So flows are popular for images. So many of the most popular flows we know, they work on image data. So real MEP, Glow, Flow++. Some examples from the Glow paper. So they are very popularly used with images and work quite well there. But what about text? There are much fewer papers talking about how to train flow models on text data. And so that's, or any type of categorical data really. So that's what we'll talk about now in a few different approaches that have been taken in the literature to this, and before we introduce Argmax flows, which is our new proposed way of doing it. So one approach is discrete flows. So that's maybe the first thing you would think of. It's what if I just make the base distribution discrete and I also make the mapping F discrete? the one that the invertible mapping. Interestingly, in this case, there is no volume term, so you don't have the Jacobian determinant. So all you have to do to evaluate the probability of your mini-batch X is pass that through F inverse to set and evaluate that under the base distribution. So the tricky part with discrete flows is how do you define an invertible transformation F that is discrete? This is very tricky. So there are two main ways that have been discussed in literature. The first is that is most natural for ordinal data, so images, audio, etc. Integer discrete flows by Hochebohm et al. They use a coupling flow, so where each transformation is transformed like this. So I mean, if everything was continuous, this would be just an additive coupling layer. But different from the continuous case is that X is an integer, set is an integer, and this mu will also be an integer. And that is enforced by using a rounding operation on this theta. And that this theta is output by a neural network. So as you might notice that there is a problem here, because how do you train this? This rounding operation is non-differentiable, and then a neural network is kind of hiding behind this theta, so we can't backpropagate into the neural net. So what they propose to circumvent this is to use the straight-through estimator, which basically, during the backward pass, ignores the rounding operation and treats it like an identity transformation. On the other hand, we have discrete flows, which was introduced by Tran et al., which works for categorical data. And the transformation looks like this. So it's again using, for example, a coupling transformation where per dimension you transform like this. And here X and Z are also integers, but they only take values from 0 to k-1. And you learn this mu and potentially also the sigma using a transformation like this. So you output again theta through a neural network. This is a continuous variable. Then you take the argmax of that. Again, this is non-differentiable. So they also use the straight-through estimator, and they approximate this by a softmax operation, pretend it was a softmax with some temperature in the backward pass. So it might seem like this is the way to go, but actually discrete flows have a lot of drawbacks. And one is that they have very limited flexibility, so they can only permute probability mass. So to see what I mean by that, if you use a factorized base distribution, so just 2 dimensions in this case, that you can represent this as a probability matrix like this, and this probability matrix will be rank 1, because you can see it as the outer product of 2 vectors like this, which are the probabilities for each of these base distributions here, or the elements of that. And so you can only, so those are rank 1 matrices, and then you can only permute probability mass, which gives you limited expressiveness. Because if you look at it kind of going the other way, if I have some target distribution down here, I have to be able to, using permutations only, rearrange that into a rank 1 matrix. And for most target distributions, there is no way to do this. So they have limited expressiveness. So what you have to do to get around this is introduce some dependency in the base distribution and not just use a factorized base distribution. So there you could, for example, use an autoregressive model, but then you're kind of back to you might as well use an autoregressive model directly for the data, because it will still.
Can I ask a quick question there, just to make sure that I'm following? So, for these discrete flows, because you need to be able to invert your function.
Yeah.
Essentially, you're describing bijective mappings only, right?
Yes. Yes.
And because you have a discrete set of inputs, the space of inputs versus outputs is identical, and because it's bijective, you essentially that's the limited expressiveness, right? As far as I understand, effectively.
Yeah. So I'm not sure I got it, but the input and output space are both discrete and the same dimensionality and everything. Yeah.
Okay, good.
Yeah, exactly. Yeah. But yeah, since you can only do these permutations of probability mass, they have limited expressiveness. So they can't represent, if you use a factorized base distribution, they can't like model any target distribution you want.
Right.
Yeah. Can I also ask something?
Yeah.
So you said now that the autoregressive coupling, it wouldn't be okay, right? Because then you would rather use a full autoregressive model.
Yeah, I guess you could use a smaller one, but yeah.
Like in normalizing flows, you have all these inverse regressive flow and master regressive flow, which are commonly used, right? So why in this discrete case do you see it as a limitation?
It's because if you want to construct a model that has fast sampling, which was kind of the original motivation, then we would want to try to avoid the autoregressive layers.
Okay.
So you can use an autoregressive flow, but it will then have slower sampling.
Okay, so like in text, you would have very long sentences, and that would become a big bottleneck. Yeah.
So then it will require, like, if you want to generate a very long text, then it will require a lot of forward passes. It's very expensive.
Right. Yeah. Thanks.
So limited. So drawbacks of discrete flows: limited flexibility. The other one is gradient bias. So both the methods I talked about in the previous slide used a straight-through estimator, and I guess there's really no way around it. You have to use some form of approximation if you want to do gradient-based training. And as a result of this, you get gradient bias. So this is an example from the IDF paper, where they show that with increasing depth of the normalizing flow, a continuous normalizing flow, so like the regular case, continues to improve, whereas the discrete one starts getting worse performance at some point. And they hypothesize that this is due to gradient bias that accumulates through the layers from this approximation. So there are some clear drawbacks of discrete flows, and it's very hard to come up with other types of invertible transformations for discrete variables, I should say. So the question is, can we avoid discrete flows? So this is a table. I will fill in some things as we go along here. So can we find another approach that does not use discrete flows? So the answer is yes. One of the approaches that have been taken in the literature is to train flows on VAE-based embeddings. So essentially, you use a small VAE. So the important part is that the encoder maps your discrete data to a continuous space, and then you model this continuous space with a flow. So this approach was taken by Ziegler and Rush and Lippe and Gaves. And so they also model text data and so on using flows. But this essentially is a VAE with like a small VAE, but with a big flow prior. And as we will show later, this works less well than what we will propose in Argmax flows, but they are closely related. So let's think of some other approaches. One thing we haven't talked about is how do you train flows on images, which is the very popular use case, and they are also discrete but ordinal. So let's first think about that and see if we can figure out a way to extend that kind of to the categorical case. So if you have some data down here that is ordinal discrete, this could be like for 1 pixel, the probabilities of the pixel intensities, and you have the flow up here, which is continuous. If you just you could try to train the flow directly on the discrete data, just convert the integers to floats and pretend it's continuous. What Uri et al. Noticed is that if you do this, it can learn to essentially place very peaky distributions just where you observe data, so around the integer values. And even without capturing any structure in the data, you can get arbitrarily good log likelihoods. So essentially, the continuous model learns to hack the fact that you have a finite set of points where you can observe data. So the method they propose to avoid this is uniform dequantization. And so what you do is just add uniform noise to the integers. So if you observe a 5, you randomly add uniform noise to that so that you get a value between 5 and 6. And so now you have support over the whole continuous space, and you don't get this collapse. And so yeah, you train your flow now just on this dequantized data instead of directly on the discrete data. And so this was mostly introduced as kind of a heuristic first. It was shown by Theis et al. That this introduces a lower bound on the discrete log likelihood. So if you kind of integrate this continuous model over these bins that have defined the different integers. So the question is, could we use this for text? So the answer is yes, but it's very unnatural because here, if these are not pixel intensities but various tokens, so they could be different. They could be different words, for example. Then there is no natural ordering of the words that you have. You have just assigned random integers to the different words. And so it does make sense to say that some word is more nearby than another word. And so it's kind of much less natural. And we also try this and we show that it works less well than what we'll introduce in Argmax flows. So we're back here. And then the answer to can we avoid discrete flows is still yes. So I didn't put the VAE-based approach in, but that could also be here. But then we have this new row, which I call surjective flows. And for ordinal data, that is dequantization that we just talked about. So the question is, can we do something similar, but for categorical data? And spoiler alert, that will be Argmax flows. But before we introduce Argmax flows, I want to talk about what are surjective flows so that we kind of understand what this is first, and that will kind of naturally lead us to Argmax flows. So it was introduced in this 2020 paper at NeurIPS last year, where we show that surjective mappings are like somewhere in between VAEs and flows. So on one side, you have bijective mappings, where every point in Z maps to one point in X and vice versa. With stochastic transformations, any point in Z can map probabilistically to some point in X and vice versa. And so stochastic transformations are essentially like VAEs. So the forward and inverse transformations for a flow is F and F inverse. For stochastic transformation, it's P, the decoder, and the inverse is Q, the encoder. And what we showed is that you can have something that is deterministic in one direction, but stochastic in the other. And we separate them into two different classes depending on whether they are deterministic from Z to X or X to Z. But our focus here will be on the one that is deterministic as you generate data from Z to X. So let's focus on that. So that's generative surjections. and they work like this. You have a transformation like this, but different from the usual invertible bijective transformations is that two inputs set can map to the same output x. And so it's not invertible because I don't know which value of set led to this x. So some examples of this is kind of written a bit in Python notation here, but tensor slicing. So if you just throw away some of the dimensions, that is clearly not invertible. You have lost information. The same with rounding, where you lose information about all the decimals. So anything between 5 and 6 gives you a 5, or at least in the flooring operation. So how do we define the inverse for this? So what we use is the fact that all surjective transformations have something known as a right inverse. And what that is a function that maps from x to set such that if I do that and pass it through f again, I get back to the same point. And this is, of course, not unique. There are multiple right inverses. And what we do is define a distribution over all the possible right inverses. And we call that a stochastic right inverse. So in this example here again, where the two points in set can map to the same point in x, when we want to invert that, we stochastically map back to either of those 2 points using this distribution cube. And dequantization that we talked about before can be seen as a surjection, where the forward transformation is one of the examples I used. It's the rounding operation. And the stochastic right inverse is this uniform distribution. So this maps to all the, like this will be a mapping for all the possible right inverses of the rounding operation. It will be a distribution over all the possible right inverses. So that takes us back here. Hopefully yeah.
So Judy, can I ask a quick question there? So you've now given us essentially something akin to, I mean, you've constructed an inverse that is an approximation of some kind, right? I'm just kind of curious, how do you see the trade-off between the attempt that you've made, that you're describing, of describing this inverse as an approximation? I mean, okay, two things. I guess you can now at least get exact gradients, right, in one direction.
Yes.
Which is useful. But what you've traded off, you've essentially traded off straight through estimator for an approximate inverse, as far as I can tell.
Yes.
I'm just kind of curious about your opinion on that. What do you think of that as a trade-off?
Yeah. So yeah, you lose. I mean, you can now compute exact gradients, or at least with a stochastic lower bound. So that is the drawback, is you introduce a lower bound on the likelihood, but as a result of that, you can compute gradients exactly, and you can also use any continuous normalizing flow on top, which is allows you to model like basically any distribution.
And I guess your results are going to show that this works quite well, which just makes me think like maybe you're suggesting that it's better to have an exact gradient but an inexact inverse operation than it is to have an inexact gradient and an exact inverse, if that makes sense.
Yeah. I guess to some extent that could be, at least if you have a factorized base distribution, then I think this works better.
Okay. Cheers.
And sorry, how do you train these surjective flows? Like, how does it change the training with respect to standard normalizing flows?
Yeah, so I mean, I didn't go into all the details there just because it would be too long, but it's you can essentially define a what we call a likelihood contribution for these layers. That is, for the bijective layers, that is the Jacobian determinant. And for these surjective layers, you will get some other term. And then you kind of, you just add that to the objective, like the log, the log base density plus the kind of where you usually have the sum of log Jacobian determinants. You add that, but you can also add this term in. But it's essentially just this. I mean, it depends on which surjection it is. In this case, it would be minus log Q. So essentially, you would add the entropy of this uniform distribution to the objective. But this is a lower bound. Yeah, so it gives you essentially an elbow. Yeah. I didn't add that part, but I think it would be.
I can check the paper.
Yeah. All right, great. So yeah, that takes us back here. So now we're ready to introduce Argmax flows. Now that we hopefully understand, like at least very roughly, what these surjective flows are. So we will introduce Argmax flows here that are more kind of a natural extension of same ideas as in dequantization, but to categorical data. So here's the illustration figure from the paper. This part is just a regular normalizing flow. You have a simple base distribution. You map it to some complicated base distribution. Here you can use any regular, like your favorite flow that is continuous. And then down here we have the Argmax layer, and this is the kind of the surjective layer part. This is in this direction computes the Argmax of this. So in the figure it's V and I call it set. There is mismatch between the notation in the two papers, but they are interchangeable. V and the set is always the same. So in this direction it's an Argmax. So that changes your continuous distribution to a discrete distribution. So if you have 3 categories, you would have one dimension in this tensor that has 3, like size 3, and then you Argmax over that part of the tensor, and you get a discrete tensor out. And since this is a surjective layer, we define the inverse as a stochastic inverse that has, so it's supposed to define a distribution over all the possible right inverses of the Argmax function, and that will be a distribution that has a support like this, where you only map to values set that is the where if you take the Argmax of that set, you get the same X back, essentially. And so this is as I said, a natural analog of dequantization for categorical data. So they have the same, like they are 2 different deterministic transformations that turn continuous values into discrete values. But this is natural for ordinal data, and the Argmax is natural for categorical data. So how do we define these encoders V? So basically, how do we define these distributions with the constraint support? So we introduce 3 different ways. I will just talk about the first one. That is quite simple. It's thresholding. So assume we first generate some continuous vector U that is the same dimension as V. Then for the value X, so this is the one that is supposed to be the largest, right? This one we keep the same, so it's an identity mapping there. And for all the other ones, all the remaining dimensions, we threshold the values such that they are smaller than Vx. So this T equals Vx. And one example of a thresholding function like this that we used is just this very simple one, T minus a soft plus, such that if U becomes larger, as U goes to infinity, this whole thing approaches T, and as it goes to 0, you approach negative infinity.
Sorry, Dietrich, I missed something there. So V is randomly sampled first. Did I understand that correctly?
No, so you first sample U. So this can be done. We define some conditional normalizing flow that samples U.
Okay.
It could also just be like a conditional Gaussian or something. But you sample some variable Q. No, sorry, some variable U, and then but you need position number X to have the largest element.
Yes, I understand now. Yeah, I see what you're saying. So you get the samples of U, and then you place constraints on those samples. I was just trying to figure out how you decide what the process of sampling U should be, because effectively you have an infinite choice, right?
Yes. Yeah. It's any distribution really, conditional on X or not. Yeah. But then it wouldn't be very useful. Yeah.
Yeah. Cheers.
Yep. Yeah, so that's one approach. And then we also introduce one that is based on Gumbel distributions and one that kind of combines these two. And just in the interest of time, I will go into those. So yeah, they are quite simple. So this is the two algorithms from the paper showing how you sample from an Argmax flow and how you optimize an Argmax flow. So sampling is very simple. You sample from, so P of V is your flow. This is the continuous normalizing flow you have defined on top. You first sample from that, and then you take the Argmax over one of the dimensions to get your discrete sample X. On the other hand, when you want to optimize it, you get a mini batch X. You condition on that, and you sample from V, and then you evaluate this, which is so this shouldn't be equal, but this is like a Monte Carlo sample of the elbow. So you evaluate that under the base distribution, and you also evaluate this minus log Q. So essentially, with the expectation, this part is just the entropy of Q. And so yeah, this is results for segmentation data. So here's the cityscapes data. So we have a downsampled so a version of that data. And we do it completely unconditional here. So we're just interested in modeling images that have like unordered categories in them. And this is samples from an Argmax flow trained on this. So you can see it learned something, reasonable. Then we also here compare our different encoders. So the soft plus thresholding and the Gumbel encoder and so on. And we compare those to rounding. So this is essentially dequantization, uniform dequantization and variational dequantization. And it works better than that. And this is likely because it's more natural, because it doesn't enforce really an order on the categories as it happens in the dequantization case. Results for text. Here are some samples. So this is using an Argmax flow with an autoregressive base distribution. So here it's what we would ideally not want, but an autoregressive flow with an Argmax transformation. Yes, and that generates quite nice samples. And then if we do the same with a coupling flow, it generates also something. I mean, you can see that it learns something, but it's not as nice. And I think that has to do with the depth. So I think we used something like 8 layers here. And I think you would need something much deeper to really capture the correlations in text data, which I think is much more complicated than what you have for images. And yeah, so here are some quantitative results. We also compare to dequantization for text data, and it also works better there, both across using an autoregressive base distribution or an autoregressive flow or a coupling flow, both on text 8 and NWeak 8. And we also compare to some other methods. So these are the VAE-based approaches that I mentioned earlier. And it also works better than those, likely because optimization is somehow simpler when you define when essentially the decoder is fixed, so you don't have like a moving target in some sense. And we also compare to autoregressive models, and they're clearly not as good as autoregressive models, but that's also kind of expected. I should say that also. There has been, or actually that is for the multinomial diffusion part, so never mind. Yes, so that concludes the part on Argmax flows, and I think I'm kind of out of time, so I will go very quickly through the second part, which on diffusion models. So this is either way shorter than the first part, but I will try to be even quicker when I go through this. So diffusion models, first introduced by Soldikstein in 2015, popularized in 2020 by Jonathan Ho and collaborators. They show that you could get really good sample quality from these models, and they also provided some connection to score-based model that people were also excited about. And since then, there has been lots of progress. So this year, from OpenAI, we saw this paper that diffusion models beat GANs on image synthesis. So GANs have for years been the best generative model for if you want to generate realistic-looking images. But now diffusion models have overtaken them in that domain. We have also seen in variational diffusion models that they get state-of-the-art log likelihoods, which have typically been dominated by autoregressive models for several years. So this is very interesting. It seems this is like one model class that does both the log likelihood and the sampling really well, which we haven't really had before. So yeah, very quickly, how do they work? You have some data distribution like this. You want to map it to a Gaussian like this. The way you do it is using T transformations. So here each transformation is very simple. It simply adds a little bit of Gaussian noise. And it has no parameters. So there are no parameters in this Q process. It simply adds a little bit of noise to this until it turns into a Gaussian. And for the decoder part, it has to learn to undo this. So it basically a denoising. It learns to denoise this gradually, step by step. And typically, I should say that T is usually something like 1,000 in most papers. So they're very deep, or lots of these noising steps. And this denoising process is learnable. So here you have some parameters theta. This is parameterized by a neural network, and yeah, you learn to denoise that. And there's lots of nice math. Not very complicated, but it would be a lot to put in the slides. But you can decompose the elbow for these models such that you can write it as a sum of terms, where each term only deals with essentially one layer. Like this. So the first and last one are special, but all the intermediate layers are essentially KL divergences between this Q distribution and the P, which is your decoder model here. And you can train these models very efficiently, since this distribution here is a closed form Gaussian, and this QT given x0. So that says that basically I know how to immediately jump from my data to any layer. I can add noise corresponding to 500 steps in one go. So you can train these by sampling randomly, which, like, for each iteration you sample some layers you will train, and then you just compute the terms of the loss for those layers, and then optimize with respect to that. And that's why you can do 1,000 layers without running out of GPU memory, essentially. So this is what I call Gaussian diffusion. So this is what pretty much all the papers have used. And that's because you have Gaussians here. And so what we did was introduce multinomial diffusion, where we simply replace these by categoricals. So it's very simple, really. The only thing that changes is what I've highlighted in red here. So our noising process is for each step, we, with some probability, randomly sample a new category. So, like, if you have a string of text, you model each character as one dimension, most of the text will stay the same, but then one of the characters you randomly, or some of the characters you randomly scramble them with some probability, and then you do this many times until you have just purely random characters at the top. And then you learn this P that learns to undo that process step by step. And exactly similar to the Gaussian case, these distributions here can be computed in closed form. So we can also train these very efficiently. So yeah, just one quick note before we look at results is that we parameterize this decoder P using Q in this way. So remember that again that this distribution is available in closed form, but it somehow depends on x0. And we parameterize P using that, where we predict x0 using a neural network condition on xt. So this just very nicely ties together the encoder and the decoder essentially, and the KL term that is in the loss becomes nicer in this case.
So Diedrich, that's essentially a layer-wise denoising autoencoder, right?
I guess you could look at it this way, where the dimensionality is the same, and
I just meant also functionally, right? Like if you use a neural network to try to map back from something that is not like one layer, essentially a one layer transformation. And
I guess in a denoising autoencoder, I guess you typically add noise to the data and then encode that and try to reconstruct the data. It's closely related, definitely.
Okay.
But here you can compute log likelihoods and so on, so it's a probabilistic generative model and so on.
Right. Yeah, good point. Yeah.
And so some results again. We did some of the same experiments for this model, and this also learns to generate something reasonable for the segmentation maps. And in terms of performance, in the paper, the way it is online now, it seems a bit worse. But somebody has contacted us and say that our implementation here, while it's correct, it's kind of it's constraining the way it's implemented. So actually, if we fix that, then we get this performance. So it's actually kind of on par with Argmax flows. And this will be in the updated camera-ready version of the paper. Text results. It generates quite nice samples. A bit what we see also for like images, it generates very nice images. And in terms of log likelihood performance, so this is the same table as we've seen before, it's just this last row has been added. It's doing quite well, or okay. It's still far away from autoregressive models and so on. But interestingly, since we did this paper, there has been a couple of follow-up papers that have developed these methods further, and they now have much better performance for text data. So they're getting closer to autoregressive models, but there's still some gap, I think. And so this is the last slide. This is just for fun to look at the denoising process. So here you can see us generating these segmentation maps kind of step by step. So there is 1,000 of these steps. So you start with some completely random, you sample from a uniform categorical up here for each pixel. And then you start running it through the learned denoising model. And then as you go down, you see some pixels are still scrambled. And in the end, it's kind of a neat image. And the same with text. So here you start with like completely random scrambled characters. And then it gradually looks more like an actual sentence. And here it's kind of almost a good sentence, but it's still not good. And then here it's, well, at least the best out of those.
Diedrich, I think I missed one thing, which is just you mentioned that you parameterized the backward, the inverse model with the neural network. But did you mention how you discretize it?
How we discretize
the output from the neural network?
Yes.
Sorry, I guess I just missed that.
Yeah, so this is a good point. I think So Emil implemented this part. So I would have to ask him, but I think what we did is this is a one hot encoded discrete variable, and I think the neural network just outputs basically some softmax, and that is our input here.
Yep, got it.
Yeah,
thanks.
So yeah, that's it. Thanks for listening.
Can I ask another question?
Yeah.
So in the case with the normalizing flows, you basically have to change standard flows into surjective flows. While
yeah.
For the diffusion process, did you just basically change the Gaussian diffusion into categorical diffusion?
Yes. So I can say something about how we how it started, because while we were working on this Argmax flows, we figured this surjective operation that maps between continuous and categorical spaces, you could essentially use any continuous model on top, right? You're not restricted to using a normalizing flow. You can use anything. And we thought diffusion models seem to be working quite well. So how about we just try putting a diffusion model on top here? And it seemed that it didn't train that well, and there were some, it was a bit unstable. And so, yeah, it didn't really work that well. But then we realized that actually you can directly parameterize it to, work with discrete variables all the time. I should also say that in this original, let's see, where is it? This original 2015 paper, they actually also mentioned that you could do this with a binomial distribution. I think they have some example on that. So it's really just that taking to multiple categories, and then of course using some tricks introduced by Ho et al. That makes this kind of work better.
Okay, thanks.
Yeah.
Can I ask a question? So you started off the presentation talking a bit about the existing methods that people use to deal with this kind of problem, and you mentioned the essentially the computational issue associated of the number of passes required to produce samples.
Yes, like autoregressive models. Yeah.
Yes, exactly autoregressive models. Exactly this slide, at the bottom right.
Yeah.
But in the end, you didn't talk much about the sampling efficiency that increases that you get from using diffusion models. I mean, it already actually looks like these diffusion models and and flows as well actually just do very well in terms of quality. So that's already a good reason to use them, I suppose.
Yeah, it's a good point, because actually diffusion models are also very slow to sample from. So it's kind of it's not really satisfying this original motivation. Although you can choose the number of discrete steps. So you can it's not determined by the data how many forward passes you have to do, but it typically to get good performance, people use something like 1,000 layers. But then there has been lots of work on speeding up this by somehow either train them directly with fewer layers, but also to kind of prune out layers after. And you can sample with maybe like 50 layers instead, and then it's still it's still much faster than autoregressive models. But that is a good point. And for flows, you can define it also any depth you want, really. So you can it will tend to be faster. At least the coupling flows we used, they're extremely much faster. I think maybe in one of the tables we had okay, so it's not here. I think it was in an earlier version of the table where we had like timings. I think it's in the appendix now. The timings of the different models, but it's much faster.
Okay, yeah, that's kind of what my that's what I figured. The flows are probably definitely could be made faster, but the diffusion models are a bit difficult because you really want to run it until there's no structure, which is quite a long process if you want to also get an accurate inverse model, right?
Yeah. So that's a good point. But yeah, so there are ways of speeding them up potentially after training to kind of construct. You typically get slight degradation in sample quality, but then you can sample 10, 20, 50 times faster. And
awesome.
Then
Thanks. I have to run, unfortunately, onto my next meeting of the day.
Yeah.
So I'll leave you guys to it.
Yep.
Ciao.
Ciao.
Thanks so much, Dietrich.
Yeah. I don't have more questions. Maybe Butch, if you have any question. Otherwise.
No, thank you very much for the presentation.
Okay. Yeah. Then thank you, Diederik.
Thanks,
I think it was very clear and very great presentation.
Great.
And yeah, and I will post this and then share with you once it's online. Okay.
All right. Great.
Perfect. Thank you so much again.
Yeah. Thanks.
Have a good day. Bye bye.
You too. Bye.